Hello everyone, I am Sasidhar Reddy. I am going to take a seminar about from the subject probability theory and stochastic process, and I'm going to discuss about the topic probability density function. Here are the subcontents of the probability density functions I'm going to be discussed. First of all, definition of probability density function, and then relationship with PDF, which is meant to be probability distribution function, and also we are discussing about expressions for discrete random variable and continuous random variable. And also let's see some few properties and proofs and basic problems. Definition of probability density function. The probability density function is a mathematical function that helps to describe the probabilistic behavior of continuous random variable. Let us assume a continuous random variable. We cannot tell the exact probability of a random variable, so that we take a function which shows the curve, and we can see the behavior of that curve and the area between them, which shows the which is considered to be property of that continuous random variable uh, over a different values of that variable. It is denoted as fx of x. Relationship with capital PDF. Probability density. Sorry. Relationship with probability distribution function. Probability density function is a derivative of probability distribution function, which is meant fx of x equals to d by dx of capital Fx of x. Wait, even I am going to be shared that uh, capital Fx of x equals to integral over minus infinity to x small fx of x dx, which is said to be a probability distribution function, is also an integral over the range minus infinity to x of small fx of x. Expression for discrete random variable. The probability density function for a discrete random variable is represented as fx of x equals to summation p of xi into del of x minus xi over I equals to 1 to capital N, where p of xi equals to probability of random variable x at xi. Del of x minus xi equals to unit impulse function centered at xi. As we discussed, fx of x equals to derivative of capital Fx of x. Probability distribution function defines for a discrete random variable as fx of capital Fx of x equals to summation p of xi into u of x minus xi, where u of x minus xi is said to be unit step function centered at xi. From the above equations, we get to know fx of x equals to summation p of xi into d by dx of u of x minus xi, where the derivative of unit step function is said to be unit impulse function, so that we get our equation fx of x equals to summation p of xi into del of x minus xi. Expression for continuous random variable. As we discussed at the definition, probability density function is mostly used for continuous random variable. So we use standard equation of probability density function. Fx of x equals to d by dx of capital Fx of x. As we discussed at the relation between both of them, PDF is integration over minus infinity to x for probability density function. Let's see the properties and proofs of probability density function. Property 1. Fx of x is always greater than or equals to 0. It cannot be negative because the probabilities of continuous random variable cannot be uh, less than 0. So they are said to be always non-negative, and the property property 2. Normalization. It is simply telling that the, the area under the curve probability density function must be 1, uh, so that the entire region cover The area of entire region under the curve is 1. Integral minus in over the every value, different values of capital X, which is said to be integral minus infinity to infinity fx of x dx equals to 1. Property 3. Relation between small PDF and capital PDF. For continuous random variable x, the capital PDF fx of x is defined as fx of x equals to integral minus infinity to small x fx of t dt, where fx of x is the probability density function of the continuous random variable capital X, where capital fx of x gives the probability that the random variable x takes the value less than or equals to small x, where it is also said to be fx of x equals to p of x less than or equals to small x. From the above two properties, we are computing that p of x less than or equals to small x equals to integral minus infinity to x fx of t dt equals to fx of x. It shows the area under the PDF curve from minus infinity to x is what defines the capital PDF. Property for PDF over an interval. For our random variable existing between two constants x1 and x2, where x1 is less than x2, the probability of random variable lies in the interval x1 less than capital X less than or equals to x2. P of x1 less than x capital X less than or equals to x2 equals to integral x1 to x2 fx of x dx. Here is the proof. As we said, probability distribution function is defined as fx of x equals to integral minus infinity to x fx of t dt, where it is also can be written as p of capital X less than or equals to x. For then, as we discussed, fx of x2 is p of x less than or equals to x2. So we write integral minus infinity to x2 fx of t dt. Then fx of x1 for integral over minus infinity to x1 fx of t dt can be defined by making a negative sign, which takes the values in reverse order x1 and it shows the interval x1 less than capital X less than or equals to x2, so that the probability between any two values in probability distribution function can be defined as capital p of x1 less than capital X less than or equals to x2 equals to fx of x2 minus fx of x1. Let's discuss some problems. See here, if the probability density function is given as fx of x equals to c into x minus 1 for over an interval 0 to x, 0 less than x less than 5, 0 otherwise find c. As we discussed at property 2, the total area under the probability density function is 1. Integral over minus infinity to infinity f of x of x dx equals to 1. As we know, sorry, maybe here there is a mistake. I think it is 0. Minus infinity to 0, there is nothing, so it is 0. From 0 to from integral over 0 to 5 fx of x dx, and x greater than 5 also is 0. This is not to be considered. Finally, c integral over 0 to 5 c into x minus 1 dx equals to 1. C into or integrating c into x square by 2 minus x for the range 0 to 5 equals to 1. On substituting 25 by 2 minus 5 by 2, It's a mistake because here it is 0. They have taken 1. It is a mistake. Let it to be considered. The final answer is C equals to 2 by 15. Here's another problem. If the probability density function is given as fx of x equals to x by 2 over an interval 0 less than or equals to x less than or 4. Find probability over the interval 1 less than or equals to random variable capital X less than or equals to 2. As we discussed at the property 4, let's use that p of 1 less than or equals to x less than or equals to 2 integral over 1 to 2 fx of x dx. For that interval, fx of x is defined to be x by 2, and substitute that function in the property. Probability over 1 less than or equals to capital X less than or equals to 2 equals to half into x square by 2, or integrating the range of in the range 1 to 2. For substituting, we get 1 by 2 into 3 by 2, finally 3 by 4. Thank you for giving this opportunity.